Okay, I think that we're ready to start. So hi, everyone, and thank you for joining us today. We're planning to discuss a very important topic today, which is called ultra-fast processes in electrochemistry, basically, which is so nicely termed also as femtoelectrochemistry in the title of today's talk. So electrochemistry, as you all know, is very complex, and it is so complex because particularly it combines so many different timescales. And they cover everything from mass transfer, such as diffusion or convection, which can be pretty slow, and all the way to the electron transfer during adsorption, chemical reactions, and electrocatalysis, for example, which is usually within the picosecond to femtosecond time range. And it's pretty much impossible, fundamentally even impossible to probe these processes, these timescales with typical electrochemical techniques. So this means that if we want to study the basic electrochemical reactions, the so-called elementary steps, we need to adopt the approaches that are much more traditionally used to probe the ultra-fast dynamics and are not traditional in electrochemistry. And for example, that is the optical pump probe experiments. So today we're hosting Professor Kramer Campen from the University of Duisburg-Essen, who uses the optical techniques, including nonlinear optics and pump probe methods, to probe the interfacial electrochemical processes. So Kramer received his PhD in 2007 at the Pennsylvania State University, which is well known as Penn State, basically. So he was a postdoc at the Vom Institute for Atomic and Molecular Physics in Netherlands. And in about 2011, he joined the Fritz Haber Institute as a group leader. And since 2019, Kramer has been a professor of experimental physics at the University of Duisburg-Essen. So Kramer, thank you so much for joining us today. Now the stage is yours.
Okay, thank you very much, Andrew, for the introduction. Let me see if I can, it always seems a small miracle when technology works. Hold on. Okay. Okay. So as was mentioned, for those of you who I don't know, my name is Kramer Campen. As was said in the introduction, I'm currently somehow a physics professor at the University of Duisburg-Essen. And today I want to tell you a little bit about experiments that we do in my group, a kind of experimental program that we pursue, where we try to do femtoelectrochemistry, try to gain insight into electrochemical, into the elementary steps in electrocatalysis and photoelectrochemistry by triggering and watching reactions that we care about with very high time resolution. The work that I will tell you about is largely experiments. This has been done by wonderful people. Gregor Swashka was a PhD student who did most of this stuff on platinum, I will tell you about, who has now gone on to work at Fraunhofer and Siemens, trying to build the world's best fuel cell. Francois Lapointe was a postdoc who did this stuff on gold, I will mention. And Yuka Yang and Marco Potens are the sort of inheritors. This is work that I have done over the last several years with Eugene Tong, who was first a postdoc with me in Berlin and now is a staff scientist with me in Duisburg-Essen. And Eugene was really the one who convinced us that we could actually do something useful. So we are sort of both of us nonlinear spectroscopy people at heart, but he had a bit of a background in electrochemistry. And I had assumed it was too hard and we would never do anything useful, but Eugene persuaded me that it was something we should do. And I think we've made at least some progress. So of course, the work rests on, we can only do the work because of funding. So we are part of a cluster of excellence in the neighborhood in the Ruhr on Solvation. There is a local so-called collaborative research center in my department on non-equilibrium dynamics in the time domain. And I spend a lot of time trying to convince them that chemistry, that chemical physics, electron transfer is that. And then I've been lucky enough to get a sort of ERC grant that supports this work. Okay, so as I said, most of the time I spend my day surrounded by solid state physicists and UHV surface scientists. And I tell them I'm interested in problems in catalysis and electrocatalysis. I'm interested in water splitting. And their first question is typically things like, well, what is this and why should I care anything about this? So what I tell them, and in fact, what I tell my parents, who are, a retired publisher and retail manager, is the following story, right? And many of you, of course, know this, but I find it good to remind myself of actually, why I should get up in the morning and come to work. And of course, the first answer is that hydrocarbon combustion is perhaps irrevocably changing global climate. You can think about hydrocarbon combustion in a sort of simplified way as the combustion of methane and the formation of CO2 and water. This was my master's in geoscience in part. You can look at CO2 concentrations in past atmospheres through firn air and South Pole snow and through bubbles trapped in polar ice. And if you do that through 1900 and even further back, what you see quite clearly is that the Industrial Revolution has this characterized by this monotonic rise in atmospheric CO2 concentration. So from sometime in the 60s, this is now directly sampled from the atmosphere in part, in the middle of the Pacific by the Scripps folks. You can then compare this data to mean annual temperature anomalies. This is just a particular data set that I've taken from NASA Goddard Institute for Space Studies. And without getting into the details of how the plot on the left is connected or not to the plot on the right, it seems quite clear that this is suggestive, and that because we have only the one Earth that we live on, it would be perhaps useful if we reorient our energy economy away from this chemistry. Of course, perhaps the most attractive possibility for a replacement fuel is hydrogen. This is, of course, because the combustion of hydrogen with oxygen is about as energy dense as hydrocarbons and produces only water. And so you would avoid the unintended climatic effects of CO2 and then the sort of degradation in environmental quality, which comes from partial combustion of more complicated hydrocarbons. But as you learn in sort of introductory physics or introductory chemistry, finding molecular hydrogen on the surface of the Earth is a challenge, right? It's too light and so escapes out of the atmosphere. Depending on where you live, if you look out your window, the largest source of elemental hydrogen is likely water, right? If you're lucky enough to live in a particularly pleasant place. And so one might say, okay, well, so why not just make molecular hydrogen from water splitting? The detail, some of the background is shown here, right? The trick, of course, is that water splitting is strongly androgonic. You need about 273 kilojoules per mole to drive this reaction. This is to be expected, right? It's just the flip side of why combustion is such an attractive fuel reaction. And it's not intrinsically a problem, right? Provided that we can get the energy to drive this reaction from somewhere else, from some sort of renewable source. It's, of course, a redox reaction, as is shown here, right? And so you can write it as a reduction half reaction and an oxidation half reaction. The reduction half reaction is the hydrogen evolution reaction. This is where we're looking if we're interested in generating H2, and the oxidation half reaction is the oxygen evolution reaction. So this is what we search for then, right? What we and perhaps many of you would like is to build a device which uses this chemistry, build a device which efficiently drives this splitting of water to produce hydrogen that could be used as fuel. When you start to think about any kind of practical device, what you immediately come to the problem that any such device requires solids that can donate electrons to and accept electrons from water. Finding such solids, though, has proven remarkably challenging, right? You'd like the thing to be active, for the process to be efficient. You'd like it for it to be cheap. You'd like, and for it to be stable. And it's remarkably difficult to find materials which meet all of these characteristics. If we're going to sort of understand the dimensions of this problem, why has it been so difficult? One way to approach this is to say, well, what are the qualitative characteristics? For example, what do we need to know about bulk electronic structure? What do we need to understand about interfacial properties or solution properties in order to optimize these physics, right? What do we need to understand about all these different aspects of these problems in order to build better devices? So it helps, at least for me, it helps to sort of ground this discussion, to look at some data, right? I'm sure all of you are quite used to looking at this kind of cyclic voltammograms. As I said, the solid state physicists I hang out with typically are not. So this is just to show you that, perhaps this most straightforward observable that one can see of the production of molecular hydrogen, molecular oxygen, is the cyclic voltammogram. This is a particular one collected in a thin film spectroelectrochemical cell on a polycrystalline gold electrode. And of course, the idea here is that if you start on the negative, the lower, this lower portion, and you scan the bias negatively, the current drops off negatively, and bubbles of hydrogen start to appear on the electrode. If you then switch scan directions and go back positively, there is this little bump at about 0.6 versus silver chloride. This is real, and perhaps the oxidation of the first monolayer of gold. If you continue positively, gold is oxidized. And if you continue still more positively, you start to oxidize water, and bubbles of O2 appear. And if you then were to come back, you would see this negative current feature. This is just the reduction of now this gold oxide. So it's quite clear, right, that in a fairly simple experiment, we can see, at least on gold, how the production of hydrogen and oxygen. Okay, but then I said, well, we want some empirical basis for understanding what material characteristics are likely to be important. So the next thing, of course, is to do the same experiment now on just, say, a different metal, and well, in this case, a similar anion. So this now is a cyclic voltammogram collected by Gregor on a platinum 111 working electrode, now in contact with a sulfuric acid electrolyte. And you can see quite clearly that this thing is much more complicated, right, than the voltammogram on the slide before. Now, if you are on the sort of negative arm, there is a little bump, a little small current feature at around, say, 0.65, 0.7 RHE. This is thought to be a phase transition in the adsorbed sulfate. If you continue still more negatively, there is this characteristic butterfly feature. This is thought to reflect now sulfate desorption and hydrogen adsorption. If you continue going still more negatively, once again, you see this scanning bias towards zero. You see this abrupt negative current feature, and this is, of course, hydrogen evolution, right? If you scan back positively, now you oxidize, you desorb hydrogen, right? And adsorb sulfate as you go back up towards 0.4. So the details here, of course, are interesting, and we will come back to some of them. But what I want to sort of, the kind of 3,000 or 10,000 meter view of the problem I want to offer now is that if you just look at these voltammograms, you can see quite clearly that it will be important to account for the bulk electronic structure of the material, right? So even if we take two metals, gold and platinum, they apparently, just from the voltammogram, have very different reactivities with respect to hydrogen and oxygen evolution. Okay, so now you can do more experiments. So I said, well, what about the interface? Well, you can compare now the voltammogram that you collect on a platinum 111 working electrode with voltammograms collected on different single crystals of platinum. So on the left is the same plot I showed you before. On the right now is a figure I've taken from Nuria Garcia Reyes and Juan Filiu from 2011. And what they show here, right, is this same voltammogram. Black is now once again the 111, red is the 100, green is the 110. And what you will note here, right, is that this thing looks very different, right? So if you, here is this hydrogen adsorption feature on the 111. On the 110, this current feature looks quite different. On the 100, it occurs at much more positive potentials. The sort of astute among you will also note that this black curve is labeled the platinum 111. Here on this plot and on our plot, it is also the platinum 111. The difference here between these two situations is that the one on the left is in sulfuric acid, the one on the right in perchloric acid. And of course, right, this is a kind of classical non-interacting anion and interacting anion as well. So what I want to get from all of this, what I want you to understand from all of this is that these voltammograms make clear that hydrogen adsorption on platinum changes dramatically with surface structure. It apparently changes dramatically with electrolyte. I did not show you any data, but there are several. I mean, it's well established experimentally that it also is strongly a function of pH. You can do similar experiments and actually look at the formation of hydrogen and oxygen, and what you find there is similar sorts of conclusions, right? That this hydrogen and oxygen formation changes with surface structure, pH, and electrolyte as well. And of course, inconveniently, changes in these two things in hydrogen adsorption and H2 formation do not necessarily correlate. Okay, so what you should conclude from all of this discussion, hopefully, is that efficient devices depend then on the properties of the bulk solid, the interface, and the solution, right? At least the interfacial solution and presumably the bulk solution as well. Okay, so if you think about this problem like a physicist, you end up drawing band structure diagrams that look something like this. Now, these sorts of pictures are quite common if you do photocatalysis, right? So if you're interested in devices directly for photoelectrochemical, say water splitting, but perhaps less common if you just think about electrochemistry. We can talk about why that might not be so, or whether this distinction is meaningful later. What I want to point out is that this is just a schematic view of the situation, right? So on the one hand, if we're interested in a metal, say in driving water splitting, we have a metal with a large density of states. The sort of top of this density of states is characterized by the Fermi level, right? When you change a bias now in the metal electrode, you can understand what you're doing is changing the Fermi level in the metal. So as you raise this Fermi level up, the energy scale here is the vacuum energy. Eventually, you drive hydrogen evolution, the reduction half reaction here. And if you lower it sufficiently, of course, you will drive the oxidation half reaction, and electrons will flow from liquid water on the right side into the metal. Life is a little more complicated, right? If you consider semiconductor materials, right? So here you have a conduction band and a valence band. Of course, you also can define a Fermi energy, but this thing there are no density of states near the Fermi energy for the ideal semiconductor. And so one is left now with a situation in which the effect of changing the bias is to bend these bands and favor the flow of electrons to or away from the interface. But the physical picture is the same, right? If you want to drive the reduction half reaction, you need to move an electron from the conduction band out into water. And if you want to drive the oxidation half reaction, you need to move an electron from this redox couple energy level down into a hole in the valence band. Okay, so this schematic picture should suggest to you that if we want to understand this, what's going on, we will need at least to understand the electronic structure of the bulk solid and any bulk loss processes. So this is mostly matters in the case of the semiconductor. This is what I have tried to show here, right? So to drive chemistry, we need to create electrons or holes at the interface. But the problem, of course, is that electrons can relax back into the valence band, and then you lose the electron in the hole, or they can recombine at bulk defects and not participate in the chemistry, right? So we need to understand these loss processes if we want to understand what makes particular semiconductor materials efficient. And of course, we also need to understand the structure of the interface. So once again, this is most relevant for the case of the semiconductor. You can form intragap states now, which can be populated by electrons. Okay, so, but this is all fine. And I've drawn these very nice cartoons, and this is the sort of favorite language of the solid state physicist. But now maybe we ask a more practical question. So just how big is the scope of this problem from the point of view of an experimentalist? So the first, well, maybe problem 0, which I didn't put on this slide, is that there are now several decades of work which make very clear that if we want to characterize this process experimentally, if we want to understand the structure of the bulk, the structure of the interface, and the structure of the liquid, and how these things come together to catalyze electron transfer, you need to do operando characterization of the interface, right? So whatever the surface states are here in this problem, they may be only stable under operando conditions. And if you pull them out of your electrochemical cell and, for example, take them to a UHV chamber, the world could look very different. So this is problem 0. But now you might say, well, okay, but all of this is fine. So I have to do operando characterization. So I'm an electrochemist, and so it's quite natural to say, well, why not just go to perhaps a bias right about here on this CVM platinum 111, where hydrogen evolution has started and is just happening slowly, and interrogate the surface and see what's there, right? Assuming we can find an appropriate operando experimental tool, why not just look at the surface under steady state reactive conditions? Of course, this is interesting and important, an interesting and important experiment to do. But our view of the problem is that this is inherently insufficient, right? The difficulty here, of course, is that you do not know from the experiment whether the species that you observe at the interface, say, under steady state reactive conditions, is an intermediate in the chemistry you care about, or whether it's some kind of unwanted side product. You don't know how the changes that you observe are related to the chemical reaction that you care about. Okay, and then yes, I already mentioned the operando part. So this is our task, right? We want to overcome this steady state characterization problem, and we want to overcome this operando characterization problem. So how do we overcome the steady state challenge? Well, our argument is that the way you do this is by doing perturbation experiments. And so the idea is shown conceptually here. We imagine a sort of idealized system where we're interested in a black reactant being converted to a blue product. And we want to understand the relationship of some purple species to the black and the blue. The claim is that if you do an experiment where you provide a pulse of black reactants to the system at well-defined times, and then you measure the time evolution of the black, pink, purple, and blue populations, that you can gain insight directly from this time dependence and the relative relationships of these species, right? So if in fact this purple is an intermediate, you would expect the black to grow and disappear, the purple to grow in and disappear, and then finally the blue to grow in as the system relaxes. If instead the purple species is a side product, you would perhaps expect its appearance to be uncorrelated temporally with the ingrowth of the blue. Okay, so obviously this idea for a perturbation experiment is quite general, right? So if the reaction you're interested in is slow and it's homogeneous chemistry, you might imagine mixing stuff in a beaker and watching what happens. Of course, if you're an electrochemist, then electrons or holes are reactants, as I tried to sort of explain on the previous slides. And so then you might say, well, I'd like to provide a pulse of electrons or holes to the system. And so one might next ask, okay, if this is what we want to do, these are the sort of experiments we want to pursue, how do we provide this pulse of reactants, and how quickly do we need to do it? And Andrew was sort of mentioning this in his attempt to give context. So this is a figure that we made from a paper that Eugen and Gregor did from earlier this year that tries to illustrate the general idea. Of course, if you're interested in electrochemical reactions, now this is the top part of the figure. You have to care about mass transport from the bulk to the interface. You have to care about adsorption and desorption processes or any sort of interfacial structural fluctuations. And then you have to care about the elementary steps in the actual electron transfer event. So you have to care about things like electron tunneling, solvent reorganization, accompanying electron transfer, or possibly isomerization. And these processes occur at this very fast end of this time scale, right? So the time scales of these, the fast time scales that we care about, if we care about this electrocatalytic problems, are somewhere in the kind of femtosecond to nanosecond range. So this would imply that if we want to do this kind of perturbation experiment that I described earlier, we'd like this black pulse to be femtoseconds long, and we'd like to be able then to follow the evolution of the interface with high time resolution, so say femtopicosecond time resolution, out to very long time scales, right? Out to the millisecond time scales. Okay, so this is all great. And you might say, well, this seems to suggest the kind of experiment that one would do. Well, how would you actually do it? And the first thing you might say is, well, why not just do this electrically, right? Let's provide a pulse of electrons to your potentiostat, put a square wave shape into your potentiostat, and then monitor what happens in the system. And you can convince yourself fairly quickly of the problem, right? This is, many of you know this, are certainly familiar with this way of thinking about it. So you can sketch a kind of simplified circuit diagram of your potentiostat, right? This is the RS is the solution resistance. So now we talk about the circuit between your reference electrode and the working electrode. The RS is the solution resistance, the CDL, the capacitance of the double layer, and ZF, the impedance. And what you find here, because this capacitance scales with area, that if you want to get very fast time resolution, you are intrinsically limited by the cell, right? You have to make the thing smaller and smaller and smaller. So you have to move sort of towards a nano electrode. And if you do that, right, you find that you can reach in practical fabrication limits timescales of, say, a nanosecond to 10 nanoseconds. At these kinds of timescales, though, other problems start to rear their head in gaining this kind of direct electrically resolved time resolution. So things like contact resistance within the cell become important. As Andrew mentioned, right, depending on how fast your reaction is, mass transport to and from the electrode will obviously screw everything up. This can really smooth this nanosecond pulse that you provide. And because typically one wants to look at very low current flows. You need a strong amplifier in your potentiostat, and somehow ultimately you're limited by the time bandwidth product of the amplifier. And all of these sort of four fundamental factors suggest that if you want to do an all electrical experiment, like say an impedance measurement at as high a frequency as you can, you're limited to, at the very fastest, timescales of say tens of nanoseconds, a few tens of nanoseconds. So nevertheless, I mean, this is interesting, right? We're interested in all these sorts of continuum of timescales. And so, of course, many folks have done these sorts of measurements. This is just a kind of summary table of the things, of the probing methodologies and the sampling speed that is they support. So as I mentioned, if you're interested in sort of pure electrochemistry, if you do impedance measurements, you're restricted to something like 5 megahertz or about 0.2 microseconds. If you do fast scan CVs, perhaps you can approach a nanosecond. If you combine electrical pumping with, say, optical probing, so do a kind of spectral electrochemistry on top of an impedance measurement, you end up with time resolutions, effective time resolutions of about 50 microseconds per spectrum. So this in part a signal to noise problem. You can, of course, trigger by other means. So there are examples in the literature of folks who have done experiments now where you try to trigger by ultrasonic bubble generation. And so the idea here is both to create an acoustic wave pattern and use this to rapidly generate small bubbles, which affect local field distributions near the electrode and mass transfer. If you do this fast enough, you can approach timescales of say 3 nanoseconds or so. A variety of folks, the Alicante group, some folks in Munich do laser-induced temperature jump measurements to try and understand the entropy of this initial interfacial layer. The time resolution in this experiment is something like a nanosecond or so per point. And of course, you can trigger reactions also by doing pulse radiolysis, right? By high photon energy electromagnetic fields driving the formation of radicals. And if you do something like this, once again, you approach a nanosecond. So we want to do better than this. I mean, we're interested, as I say, in triggering and probing with these kinds of time resolutions. So how do we trigger and probe? Well, our approach is to trigger and probe reactions with femtosecond optical pulses. So in each case, so we use lasers, which now produce optical pulses at a variety of photon energies, which are something like 40 to 50 femtoseconds long. You can play tricks if you want to make them shorter. And these pulses then initiate the reaction in ways that I have alluded to above, and we'll come back to below. And then we try to probe the interface with high time resolution. And we do this in two ways. The first is to use a flavor of nonlinear optical spectroscopy called some frequency generation. I've shown here a vibrationally resonant version of the technique. So we ignore the purple laser pulse in the left-hand diagram for a second and just focus on the green, red, and blue. So if you want to do a some frequency measurement, the way that you do this is to overlap spatially and temporally the output of two pulsed lasers at an interface, and then monitor the emitted photons at the sum of the energies of the two incident beams. This emitted sum frequency field is useful because it is interface specific by its symmetry selection rules, and because it is a spectroscopy. So as you tune one of the three relevant photon energies in resonance with an optical transition, you see a multiple order of magnitude increase in emitted intensity. And so you can make an interface specific vibrational spectroscopy, an interface specific version of infrared or spontaneous Raman by making one of these incident pulses in the infrared, but you could also make it interface-specific UV vis absorption by moving one of these pulses into the visible. So now we use this technique to study electrocatalysis, and the way we do this is by doing this kind of spectroscopy inside a thin film spectroelectrochemical cell. So this is what I have tried to show here. Okay, so in addition to the optics part, we have also recently got excited about optoelectronics. So the idea for one optoelectronic experiment is shown here. So one has two pulses, right? The first of them drives a reaction, say an electron transfer into solution. And then the second pulse resonantly interacts with whatever this transient species is. So, and then one, as a function of the photon energy in the green pulse, measures the readout of the voltage or current from within this spectroelectrochemical cell. So on the one hand, we probe with high time resolution using some frequency generation, using this nonlinear optical technique. On the other, we do so using this kind of 2-photon photovoltage or 2-photon photocurrent readout. These two probes are complementary. So in principle, right, they reveal the same, they probe similar quantities. Of course, this 2-photon photovoltage does not have the selection rules of this some frequency spectroscopy, but it's still useful, right? So it's useful on the one hand because ultimately what we care about is the interaction of light into producing current out of the cell. And so this allows us to directly link the species we are probing with a measured current or voltage. And on the other, because, so for example, if this thing is a metal electrode now, if you irradiate it with an optical pulse, of course, this drives changes in the metal, which are not the chemistry that you're interested in. And so probing with photovoltage allows you to avoid having the optical response of the metal in your measurement. Okay. So in what follows then, I want to tell you sort of two stories about hydrogen evolution. So progress, our sort of current understanding of hydrogen evolution, or the progress we think we've made in understanding hydrogen evolution on gold, and then hydrogen evolution on platinum. I should maybe say here before I go any further that when Andrew first asked me to do this, I wrote a sort of quite general abstract at the time without thinking in detail about what I'd say, because this was several months ago and the world could end and I wouldn't be giving the talk anyway. So one, don't think too much about it until it comes. And then when I sat down to make this talk, it became immediately obvious that I could not tell you this story about metals and this story about semiconductors in 1 2-hour talk. And because I did not want to sort of, force people to stay here for 4 hours, I thought we should just focus on the sort of simpler metal physics before first. But I am happy to talk with anyone about the semiconductor problem as well. Okay, so what I want to do now is tell you this story about the first steps of hydrogen evolution on gold, we would argue. At that point, we will take the intermission and we can, questions can be asked or, people can get a drink or whatever. And then I will come back and tell you about the situation on platinum. Okay, so I told you we want to start hydrogen evolution on gold with femtosecond optical pulse. This cartoon here is meant to provide a little bit more detail about exactly how we do this. So on the left is the band structure of gold. Right now I've filled in the D band and the S band and the Fermi energy. This green arrow here is meant to show you to scale, right? window of water stability. The relevant redox couples are shown out here in blue, and on the right-hand side of the diagram is platinum. We will come back to this later. So because gold is fairly inert, right, there are no surface states in this problem. And if we want to rapidly drive this chemistry, we need to do so by inducing adiabatic transfer into the conduction band of water. So the idea here is that we irradiate the sample with a pump pulse in the UV at 4.65 eV, and that this is sufficient now to promote electrons, some fraction of the electrons near the Fermi energy, and drive adiabatic transfer into water's conduction band. At this point now, this is a delocalized electron. It should localize. We will talk about all these physics in the next few minutes, and then presumably drive this kind of chemistry here. Okay, so this is just now a cartoon structure. So as I sort of repeating what I've just said in different words. So as was apparent in the CV, right? Platinum is fairly reactive with hydrogen. So you always see these current features assigned to hydrogen absorption between the hydrogen and oxygen evolution. This is so-called underpotential deposited hydrogen. So if you care about the generation of H2 from platinum, you need to understand the platinum hydrogen bond and how this then combines, right? Either recombinatively or through a species in solution. On gold, of course, the situation is quite different, right? There are no features on the voltammogram corresponding to hydrogen evolution. And therefore, these folks have argued through some DFT calculations in part that at least the first electron that you transfer to induce hydrogen absorption proceeds by an intermediate that is sort of particularly solvated electron. So we take this kind of cartoon to suggest that if we want to understand the first steps of hydrogen evolution, of hydrogen absorption, and then H2 formation on gold, we need to be able to generate and characterize this interfacial solvated electron and perhaps look for this local structure. Okay, so I told you we do this via this 2-photon photovoltage technique. So the way we do this, the kinds of experimental data, this was sort of an accident that we discovered that this worked. We were very pleasantly surprised, and so it may not be obvious to you when I tell you what the sort of observable is. So all that's been done here is a very simple experiment in which you clean this polycrystalline gold electrode, you assemble the cell, and then you leave it at open circuit voltage. And this time now on the x-axis is seconds, because this now is just what is being read off the potentiostat. So as many of you know, there's 1,000 different things that can influence open circuit voltage, but if you're a bit careful and people don't breathe too hard on the sample, the thing stabilizes over a few minutes as shown here. So at the same time now we create this pulse train of UV pulses. And what's happened at 600 seconds is that we unblock this pulse train. So we have a kilohertz laser, there's one every millisecond. And now you immediately see a jump in open circuit voltage of about 300 millivolts, right? After some sort of relaxation, some sort of equilibration, once again, this open circuit voltage is stable. Okay, so you might say, well, there's 1,000 different things, of course, that can change open circuit voltage. So how do you know that this, you're not heating the solution, you're not driving photochemistry in bulk liquid, you're not in anything else you can think of? So we do a bunch of experiments, a bunch of control experiments to try and constrain this. The first thing to note is that for the pulse fluences that we use, focusing the ultraviolet in solution produces no signal. So we have very precise control of the height of the interface. It can sort of march our focus through the solution down to the surface. We also measure the pH of the solution. So if you let this reaction run, If you just let this cell sit for a while and run it in a flow-through geometry, the outflow becomes progressively basic as the reaction goes, or as it's left, as you would expect if you're producing H2. And maybe most interestingly, if you now collect a CV under illumination, you can see hydrogen oxidation features on gold, right? So if we now scan negatively in the presence of the UV and now scan positively, you see this very clear hydrogen oxidation feature, which is otherwise absent from gold without the UV. And so we take these things to suggest that whatever the UV pulse is doing, it is specific to the interface. It has a pH. It drives a pH change in the solution, which is consistent with hydrogen evolution. And the voltammogram suggests that it produces adsorbed hydrogen, which can be oxidized by scanning positively. Okay, so this is the first pulse, but of course I told you we do 2 photon photovoltage. And what you do here now is you wait till the sample is stabilized, say up here at about 1,000 seconds. And now you add a second pulse train at a variable photon energy. And if you do that and scan the thing as a function of delay between 2 pulses. And if you do that, you produce data that looks like this. So once again, this is just the seconds right off the potentiostat. And each of these spikes correspond to a different delay between this UV pulse and a pulse with different photon energy. So we want to argue then that this is consistent, this kind of data is consistent with the second pulse resonantly exciting an interfacial species. Okay, so maybe a quick intermission. So I told you we're interested in this solvated electron. And if you're not in this business, you might say, this is crazy. What is a solvated electron anyways, right? Water is not full of electrons. And it turns out that the solvated electron in water has been studied for a long time. You can create it in any number of ways: by single photon ionization from some molecules, by multi-photon ionization in liquid water. Regardless of how you create it, the physics afterwards are pretty similar. So one initially creates a delocalized solvated electron. This is something like a conduction band electron in water. And from the instant of formation, this thing sort of continuously localizes. So this delocalized in a particle in a box picture, this delocalized electron would have an optical absorption, a Drude-like optical absorption. So at DC frequencies. In practice, it's been measured at something like 1 terahertz. If you let it go in time, now it continuously localizes, and after about 150 femtoseconds, 200 femtoseconds or so, one sees now an optical feature that is fairly narrow and centered at about 720 nanometers. So this is now just data from an older PRL now by Migas and friends. And what you see here is the delay between the pump and probe pulse, right? So the pump pulse creates the solvated electron. You see at 0 picoseconds at time 0, there is an absorption which is peaked far in the infrared. This is what I have described here in point number 1. And as you go forward in time, you lose intensity at long wavelengths. And by 700 femtoseconds or so in this case, you have this very clear spectral feature at about 720 nanometers. Okay, so these are the events following, but you might say, well, obviously water is not full of electrons. So what is the ground state lifetime, right? How long do these things live in solution? And they live a surprisingly long time. So let's say tens of nanoseconds or so in bulk liquid water. It depends a little bit on whether there's anything else present in solution. Okay, So this is the background to the optics of the solvated electron. And now we've done this experiment, and Francois and Eugene do it at many different time points and vary the photon energy now of this second pulse. And if you do that and extract the amplitudes of this 2-photon photovoltage perturbation, you can create a spectrum. So now on the y-axis is the 2-photon photovoltage change. This is the 2-photon perturbation to this open circuit voltage. The x-axis is the photon energy of this second pulse. So for those of you who like wavelengths, that's the top. For those of you who like energies and EV, that's the bottom. And each of these curves now are at a different delay point. So you can see at -1 picosecond. So that's now where the resonant probing pulse comes before the UV by a picosecond. There is no 2-photon photovoltage signal. That's the dark blue line. But that as you approach 0, you gain a lot of signal at long infrared wavelengths, right? So we went as long as 4,000 nanometers, but whatever this feature is, it's clearly peaked way off at long wavelengths. If you now go past 0 to positive wavelengths, so now we move to the right-hand panel, what's apparent very quickly, right, qualitatively, is that as you go to positive times, that first this absorption at long, in the first, say, 100 femtoseconds or so, this absorption at long wavelengths grows in, but that you rapidly lose intensity here and instead gain some intensity at, say, around 800 nanometers in wavelength. So this is what's shown here. Okay, so this is the qualitative sense of the data, but you might say, well, what happens? What does this mean? Well, we think this is consistent now with a scenario in which this interfacial solvated electron, the delocalized species, localizes on a time scale of, say, 300 femtoseconds. That's the time scale in which you lose this intensity at long wavelengths. This is bulk-like. At longer times, you still see this narrow feature at much higher photon energies, but it is clearly redshifted from bulk, right? So in bulk, this thing is at 720 nanometers, and our spectral resolution is not the greatest for practical reasons that we can discuss, but wherever the peak of this feature is, it's definitely to longer wavelengths than this 720 nanometers. It is also true that you have intensity at 720 nanometers, even at 0 picoseconds. So some electrons appear to localize almost immediately at time 0. Another interesting aspect of this data is that the thing shows a clear polarization dependence. So if you probe at very at short times, at low photon energies, at long wavelengths, there is no polarization dependence, right? So you can change the polarization of this second pulse. If you do probe now at the higher photon energy, so this localized state, you see a clear polarization dependence, right? Somehow the symmetry of whatever this resonance thing is changing in time. Oops. So you can, if you're interested, and we can talk about this in detail, or you can, the paper came out last year, you can quantify all of these details. The point here now is this is just a schematic of what we think is happening in the experiment. This excitation pulse creates a population of hot electrons, some of which relax in the metal directly, some of which are transferred either into the conduction band or into a kind of trapped hot electron state. This thing relaxes on a time scale of about 820 femtoseconds and forms the local solvated electron, and on a time scale of, say, 50 picoseconds or so to drive product formation. And of course, electrons can return to the metal without driving chemistry. Okay, so this is the solvated electron part. This is where we want to get eventually, but clearly to get there, we will also need to say something about water structure, right? If we want to look for this solvated structure. So here there will be no time dependence, right? This is our progress on this secret. We want to say something, at least demonstrate that we can say something about steady state interfacial water structure using our probing techniques. So this is a problem, of course, that has been studied for a long time. You can do it, this kind of textbook picture is shown here. One would expect that at a negatively charged electrode, right, the water should be pointing down, hydrogen should be pointing down, and at a positively charged, hydrogen should be pointing up. There's a paper now a number of years ago, an X-ray reflectivity paper from Tony and friends, coworkers, which inferred an oxygen distribution function, which seemed to be consistent with this picture, right? So this is now, they used a silver 111 electrode, and we're at below and above the potential of zero charge. And this is what they found, right? So they would argue that this data is consistent with the average water orientation flipping around the potential of zero charge. This paper was from 1994. It's clear, I think, now from a variety of increasingly complicated theoretical studies that this effect is apparent in theory, but significantly attenuated, right? So one really has to average over all sorts of fluctuations in order to see this. And if you integrate under these curves here, one would infer that the interfacial density increases by something like a factor of 2 as one goes from negative to positive potentials. So that in this oxygen down configuration, this first layer is much, much more dense. This effect, if it exists in theory, is much, much, much smaller. Okay, but this is just now water densities. And you might say, well, the important point about water, I've always been told, is the hydrogen bonding network. So what can we say about how the hydrogen bonding network changes with changing potential? There was a study now in 2014 that tried to address this problem that appeared from Mikhail Salmaran and co-workers. So this is a combination X-ray absorption and ab initio molecular dynamics. And their contribution now was to identify 4 possible different types of water molecules. So now these interfacial water molecules, one is this so-called non-donating, where both OHs are pointing down. One is a single donor parallel, where it's donating, interfacial water is donating one hydrogen bond to other overlying water molecules, and it's parallel to the surface or quasi-parallel. There's also this single donor perpendicular, in which an OH points towards the metal and the other OH donates a hydrogen bond, or a so-called double donor. And so what they see then, so in experiment then, it turns out to be sort of challenging, right? Because there are no non-donors, and the double donor and single donor perpendicular are not visible in this X-ray probing scheme. What you find if you now compare experiment and theory is a picture that's shown here, right? That as you go from negative to neutral to positive with respect to the potential of zero charge, that the amount of the single donating species decreases with this potential change, right? And this is at least now just consistent in sort of approximate terms with this textbook picture of changing water orientation. But of course, from our point of view, it's kind of insufficient, right? So we, in particular, we're interested in understanding this single donor perpendicular. So if we take this kind of cartoon seriously, it will be these OH groups that point down towards the metal, which play a particularly large role in solvating the interfacial electron. And so we'd like to develop an experiment, at least, which can probe this particular type of interfacial water. So we say, okay, great, we know how to do vibrationally resonant some frequency spectroscopy, and we know how to tune our infrared photon energies to the OH stretch. And so we should be able to say something about interfacial water by looking for the spectral response of interfacial water at its OH stretch. And so we do this inside the thin film spectroelectrochemical cell. This is technically a sort of significant pain in the butt for reasons that we can discuss if you're interested in the experimental details. Okay, so I told you that to do this experiment, one spatially and temporally overlaps, in this case, the output of a pulsed non-resonant laser at 800 nanometers and one in mid-infrared. And if you do that, what you find is the black line. So for a polycrystalline gold electrode and a 1 molar perchloric acid. And this immediately is somewhat disheartening, right? But if you start to think a little bit about what's going on, it becomes clear. So we need to bring an infrared pulse through a layer of water and reach the electrode. And of course, liquid water has, well, lots of water, and this water absorbs at OH stretch frequencies. And what is happening is shown here, right? So this is the spectrum of our infrared pulse before it passes through the water. And you can see quite clearly that none of the photons that enter the cell are actually reaching the interface at, say, 3600 wave numbers. It's all eaten away by water absorption. In contrast, when you get up here to say 3,800 and 4,000 wave numbers, they're basically all getting through and generating some frequency off of the metal. And this is, of course, to be expected. The bulk water OH stretch is peaked at, say, about 3,300 wave numbers and decreases as you get now down to about 36. But if you squint very carefully at this, you would say, well, if I really look here, it looks like there is something, right? There's maybe a little wiggle in this line. And perhaps this is a spectral feature. If you do spectroscopy, one way to think about this is maybe it's a phanoresonance, right? A narrow spectral feature from the molecule, from an interfacial OH that sits on top of a broad background from the metal. And if you know what a phanoresonance is, right? A broad background means that its dephasing is very rapid. And so you can imagine now, if I can sample this thing in time, so slightly delay the infrared pulse with respect to the visible pulse, the metal electron response will have dissipated and only this interfacial molecular response will be left. And so this is what's done here on the right. If you delay by about 550 femtoseconds, you end with this narrow feature. So this thing now is consistent with what we would expect from a weakly hydrogen bonded water molecule, a weakly hydrogen bonded OH stretch. So one sees similar spectral features for water at hydrophobic interfaces or water at the air-water interface. So of course you need to do control experiments so it disappears in D2O but is present at OD stretch frequencies to convince yourself that this thing is at least plausibly an interfacial free OH. If you care about the optics, we use short pulses, and of course one of the effects is that this thing is chirped as this infrared pulse is chirped as it passes through water. So different colors pass through water at different speeds. And so this, one might imagine, could also contribute to spectral artifacts. So you can satisfy yourself that this is in fact not our signal by looking at collecting the spectrum now as a function of delay between the two pulses for the gold water interface that's on the left, and for the quartz water interface, in which no weakly hydrogen bonded interfacial OH is expected, on the right. And you can see quite clearly that this strong feature that we see at 3700 is largely absent on quartz. So all of this sort of suggests to us that we can really see this single donor perpendicular. So now you can do spectroscopy of this as a function of potential, because we're inside an electrochemical cell. And if you do that, several things become immediately clear, right? The first is that there is no stark shift. So as you vary potential, the spectral feature doesn't shift. This is, of course, okay, right? This is consistent now with the single donor perpendicular species, which is interact, and the frequencies at which we're measuring, which suggest a really weakly interacting OH. Curiously, you also see that this intensity of this feature, so this is now plotted in the bottom, this is just the integrated intensity, increases from below the potential of zero charge up to oxide formation, right? So it increases below till you reach the potential of zero charge. It's pretty flat up to where you start to see the oxide, disappears as the surface is oxidized, and only reappears now as the oxide is reduced. But there is no hysteresis, right? The system is very reproducible, and you can do this experiment as many times as you want and see the same kinds of features. Okay, so where does this leave us here? Well, we would say we have probed this perpendicular population in situ at the Goldwater interface, Operando, changing potential from this below the potential of zero charge to above is consistent with the scenario in which the population of this species is increasing. This is in disagreement with theory that suggests that at least the relative population of this species decreases. So our results then imply that the absolute population must increase over the same potential range, perhaps consistent with increase in water density or somewhat different hydrogen bonding definitions as a function of potential. Okay, so this was from a few years ago now. Now we are working on trying to put these two things together, right? So we are almost to the point now at the next step in this, where we will try to generate the electron and then explore how water structure changes with electron generation and localization of the electron. Okay, and so this is all I wanted to say. Ooh, slightly longer than I thought. Maybe we just take 5 minutes here or so, and then I will come back and tell you some things about platinum. Perhaps I will shorten it in real time.
Thanks, Kramer. We're open to questions, so please go ahead and ask if anyone has any.
I mean, the comments are also appropriate. So like things like that made no sense at all would also be completely reasonable.
Maybe I can start then, Kramer. So
sure.
We in the previous semester, we also hosted Anders Nilsson, who works with X-FELs, the X-ray free electron lasers. So we discussed the water itself and how the water behaves and how you can probe it. And one of the things that I was thinking since then is how easy is it to apply the X-FELs to electrochemical interfaces? Of course, there are many complications, but at the same time, the way it should be applied is in a pump-probed manner, obviously. So how do you see, so if we could apply that, so do you see that we could get a lot more information, like element-specific information?
It's complementary, of course, right? I mean, ideally, we should have all these kinds of information. I mean, so let's I mean, the sort of dream is that you would like to be able to follow the electron on its path, in this case, from the solid all the way through to the liquid, and understand the correlated configurational changes that happen, right, along each step of the way. And so this necessarily implies, I think, that one would like to have multiple probing schemes that operate over a wide range of photon energies. Right, so you would like to have low photon energy resonances. So I described something in the mid-infrared, but it would of course be nice even to probe low frequency vibrations that tell you something about collective modes, right? And the response of collective motion to generation of chemical products, right? Or And so I think they're each complementary, I guess, is the short answer to this problem. I mean, the technical challenges, I would say, are only heightened exfil, right? Like this is, you need to, so I did not discuss any of these details, right? But if you want to build sample cells where you can actually do this, it's somewhat non-trivial. So you need to be able to bring the radiation that you want, of the photon energy you want, to the interface, and it should not have too large an effect in the electrolyte away from the interface, because otherwise, like, what are you're not probing the process of interest. And so finding the right combination of the right geometry of electrodes to do this is non-trivial. So for example, in this case, maybe we just, from my work, can be illustrated. So I told you for this case of this gold electrode that all of this infrared intensity was lost because I want to bring the light in through water. And so one might say, well, why not come from the back and bring the infrared through some transmissive medium from the back? And of course, this is challenging in gold in particular, right? So we had tried to do this initially, and you can calculate the transmission and reflection coefficients. And if you do that, what you find is that if you want to do this in general, you need a layer of gold on top of a prism or something that's about 4 nanometers thick. And so we tried to deposit then a 4 nanometer thick layer of gold on top of maybe a few nanometer thick layer of chromium to make wetting work better. And it's very difficult to get a stable surface that is stable under potential cycling under those configurations. You can get around this if you want, if you do in a geometry of total internal reflection. So this is like an ATR, FTIR cell. But of course, then the problem here is that it's extremely sensitive to the angle of the incident light. So things become much, much more delicate experimentally. And so this is why we have mostly worked in this thin film geometry. Maybe another, sorry, I get excited. So maybe another point along these lines is that now I just list the problems, right? So if you want to do this now and come through a window material, you need a window material that is IR transmissive and is ideally stable in, half molar acid or half molar base. And of course, all of the common IR materials, all these ionic crystals like potassium bromide and things like this, eventually they dissolve in half molar acid, right? So you are left with some situation now where you're working against the clock in an attempt to do reasonably clean electrochemistry and still do the spectroscopy. We sort of accidentally stumbled on the possibility of using a diamond window, which has the advantage of being very stable. Of course, in acid, there's one Raman feature, one absorption at longer infrared wavelengths. But of course, this is a kind of special occasions thing, right? I tell the guys that if it costs us 3,000 euros per cell, this is like we should really be sure.
Of course, no. It's what I was trying to ask is if you see any significant advantages or any new information that we can learn if we have X-rays, soft X-rays as an incoming beam.
Sorry,
and then we combine it with IR, say.
It's quite clear that you want information about the valence electrons, which you can most directly access from different aspects of the X-ray response.
Sure.
So it would be nice to do X-ray absorption. It would also be nice, there are a couple of experimental schemes you can imagine where you could do photo emission. So you could detect emitted electrons. So to do this, you need to make, the way to do this is to make a kind of nano pipette electrode, which has a meniscus, right, that extends out. And the reason why you might want to do this is because this offers the prospect, electrons carry more momentum than photons do. So this offers the prospect of momentum resolution. So why would you want to do this? Well, if you think about the passage of an electron from a metal into solution, The distinguishing factor is that the metal has this, the sort of qualitatively, is that the metal has this enormous density of states where the electron is delocalized, and then it has to localize in order to drive chemistry, right? And if you can resolve the electron's momentum in a kind of time resolved way, it offers the perspective that you could actually observe this localization in real time, right?
Mm-hmm. Okay, I have one more question regarding, so I think that probably the best would be to go to slide 16, where you show the first time the data, the cumulative data that you collected. So when I see this kind of plot, I understand that there are many different things that were changing, like the delay, and then you measure the potential. Is there any way, or maybe you can foresee any way to fit this data with real model that would account for certain processes, at least in a rough way, but not just taking the quantities that you measure out, and such as a delay, but also fit it, because the data looks like something you can fit.
So the pattern to the data reflects so as I said, maybe a note about this experiment. So this experiment is the dumbest, it's the most sort of naive experiment possible. So as I said, the laser runs at 1 kilohertz. So you have a femtosecond pulse every millisecond, and this potentiostat is just open. Mm-hmm. So there's something like a 12 order of magnitude mismatch between the sampling of the potentiostat and the laser excitation. Mm. Right. So now we work on better detection schemes, trying to be somewhat smarter about this. So it was very surprising that this would work at all. So now you say, well, okay, what is this? What do the details of this data depend on? And of course, they depend on all of the details. So if you change, for example, they depend on cell hydrodynamics. So if you change the thickness of this water layer, if you change flow rates, you can change the overall shape of how these things look. What appears to be insensitive to all of this is this, is the extracted amplitudes size of this thing, this 2 photon thing, and this is maybe sensible because most of the things most of the physics that you can imagine which could influence this, or the chemistry which could influence these transients, don't occur on this kind of picosecond time scale, right? They're so slower.
This is just the echo of what happened, basically. Right.
Yes. Yeah. Right. Sort of filter. Yes. Exactly. Right.
Okay. Maybe one more question, and we'll continue if no one else has any questions so far. One regards your methodology is very close to what people call the laser-induced temperature jump, like you mentioned previously.
Right.
But you said that you're trying not to induce the temperature jump. But let's suppose you do it intentionally. So you use the first pulse to induce that temperature jump, or maybe you add a third pulse. Is there something else that you can learn? You can probably extend the experiments into sort of a new direction.
Right. So these guys, the experimental config. Okay, so maybe a brief note about what's actually happening when you do this kind of excitation. So when you do this optical excitation, what happens initially is that you create electrons and holes in the metal. These recombine on a time scale of like 4 or 5 femtoseconds, at least in UHV and photo emission measurements. At that point, you have an athermal population of electrons. These thermalize then on timescales of, say, a few hundred femtoseconds. And then the electronic system equilibrates with the phonons, with the vibrations, on a timescale of, say, a few picoseconds. So these kinds of timescales are apparent if you do optics directly off the metal. So if you remove the water and do this kind of pump, and then reflectivity changes of the metal. if you want to do now this temperature jump experiment, the way that people do this is to use nanosecond pulses and pump from the back of the electrode.
Mm-hmm.
So the idea there then is that you obscure all these fast physics and are left only with the heating of the electrode at the end. Now, of course, so the version of this experiment that people report is the changes in electrochemical observables. But of course, you could also do spectroscopy of this, right? So if you wanted to understand what are the microscopic changes that accompany these entropy changes, a natural way to do that would be to use that kind of pumping scheme or something similar, where you thermalize the entire excitation, and then probe the spectrum of, say, interfacial water or interfacial electrolyte. And one might imagine, I mean, there are folks, I think I saw Wolfgang Schmickler around. He will have I'm sure he has lengthy opinions about this. But I mean, it is at least plausible on its face that you could imagine, for example, that the change in interfacial entropy, the potential dependent change in interfacial entropy, the mechanism of this change could be very different as a function of bias. It could depend on spatial characteristics of the electrode. And in principle, this kind of probing scheme offers you access to that.
Mm-hmm. I see. So you can combine the first pulse that is thermally excites the surface and heats it up with the some frequency generation approach.
Sure.
Which is the two pulse afterwards.
Yeah, this is
not a big problem. Okay.
I mean, you just need a long optical delay line.
Oh yes, yeah. Okay. Well, if we don't have any more questions, I think we can continue.
Okay.
Thank you.
I will. Okay. Sorry, I talked too much. Okay. So as we sort of touched on a little bit before, if you want to understand hydrogen evolution on platinum, the situation will be very different than gold, right? So in contrast to gold, now at potentials positive of hydrogen formation, so say between 0.1 and 0.3 or 0.5, depending on the surface on this plot, one sees the adsorption of hydrogen on the platinum surface, and presumably H2 is formed either from this recombinative desorption or from this so-called Herofsky mechanism, this combination with a proton from solution. What I want you to get from this cartoon is just the point that if you want to understand hydrogen evolution on platinum, it is quite clear that you need to be able to understand what's going on, what is happening to this platinum hydrogen species. So the first thing that we tried to do then is demonstrate that we could probe this, and we also did a vibrational spectroscopy here. So once again, the idea is to do a vibrationally resonant some frequency probe, in this case, looking for the platinum hydrogen vibration of a top adsorbed hydrogen. So some data now from this type of measurements are shown here. So now the x-axis is, as in the case of water, now the IR frequency and wave numbers, the incident IR pulse. This thing is broadband and covers nominally between 1900 and about 2300 wave numbers. It is this range where we expect, based on mostly prior work in UHV and some prior electrochemical work, to find this top adsorbed hydrogen. Anyways, if you do the measurement now, this is the steady state measurement as a function of bias on the platinum 111 single crystal, and you pay particular attention to preparing the surface as cleanly as possible. What one sees is something that looks like this, right? So there are two spectral features that are apparent. And clearly they grow in at about the same rate as one decreases bias and moves closer and closer to hydrogen evolution. If you collect spectrum in this frequency range from the double layer region out here, there is no signal, as you would expect, right? So there's no hydrogen adsorption out there, and therefore no platinum hydrogen vibrations. The situation looks quite different on platinum 110. So here, one sees perhaps the same spectral feature and two additional ones as well that I've labeled alpha and beta. There is some interference, spectral interference going on here. We can discuss this in depth where that might come from if you're interested. This is a consequence of this being a coherent optical spectroscopy. And you can see quite clearly, right, that while the voltammograms are not nearly as pretty as the ones in the meniscus geometry that we collected before, this is perhaps to be expected for minimal contamination from the window, but mostly because to do this measurement, we make this gap very small, and it is very challenging to do reasonable voltammetry under situations where you have this very thin film of electrolyte above the working electrode. So anyway, what I want you to get from this is that it is quite clear that the spectral features in this range change with surface structure. Broadly, if you squint, the in situ CV show expected current features. You can then go in and look at these peaks. If you do it for 110, you see that there's quite a clear stark shift of these peaks as you go through the UPD hydrogen region. You have to do some fitting. We can discuss the details of this to really extract this. And of course, the worry of most electrochemists who I talk to about this data is that the thing suffers from CO contamination. And so you can satisfy yourself that this is not the case by doing the experiment now in D2O instead of H2O. And now this spectral features are shifted what you would by a factor of 1.41 or so, as you would expect, and are also frequency dependent. Now, of course, the absorption cross sections of this, the spectrum don't look the same, but this is perhaps sensible or at least understandable because the absorption cross-section of this deuterated species need not be the same as the hydrogenated one. So I do not have time to get into these details. Let's just say that partly in conjunction with theory and from some control experiments in comparison to UHV, you can assign these spectral features to particular populations of a top adsorbed hydrogen. We do so for the platinum 111 surface and argue that this lower frequency one is the 111 facet, that this higher frequency one, which is easily perturbed in the presence of salt, is a kind of solvated proton interfacial species, and that the more complicated spectrum on the 110 is the result of a 111 defect and this so-called 111 microfacet that exists on the crystallographically the crystallographically perfect 110 surface. So what does this leave you? Where does this leave you? Well, the sort of qualitative conclusions that you can draw, I think, which are independent of the details of these assignments, are that from the beginning of this UPD hydrogen region, so as soon as hydrogen is apparent electrochemically, we see a top adsorbed hydrogen, whether it's on 111 or on 110. And at all of these surfaces, we also see multiple types of a top adsorbed hydrogen as well. Okay, so this now point one just summarizes what I just told you. We observe top absorbed species and perhaps this interfacial hydronium at all potentials through UPD. In UHV, it is clear that hollow and perhaps bridge sites are energetically favorable. This is also what most theory tells us. I would suggest that we can reconcile 1 and 2 by suggesting that on macroscopic timescales, at least, there is exchange of this atop adsorbed and other types of adsorbed hydrogen. We are building an experiment now to probe this hollow site adsorbed species. Okay, so we think we can see platinum hydrogen. The next thing I want to demonstrate is that we can drive the reaction. So what we think we can do now, so in gold, there is no strong adsorption. The situation is quite different on platinum. So instead of having to reach the solvated electron, we have these surface states at much lower energies. The idea is that by a lower photon energy pump pulse, we can partly excite this platinum hydrogen antibonding orbital and hopefully drive hydrogen evolution. So the first thing then that we wanted to sort of demonstrate is that if this is true, perhaps this optical excitation would induce charge transfer that we could detect electrochemically. So once again, this is the same cartoon that I've shown you before. Now we're looking at the right side of the diagram. And we have now bonding and antibonding states, right, within the range over which water is thermodynamically stable. And so we use a 1.55 eV photon energy pulse. It's bigger than the water window, so it should be more than sufficient to try to populate this antibonding state, and with the hope of triggering hydrogen adsorption, desorption, and H2 formation. Okay, so we're not so clever, right? We tried to start with the simplest possible experiment we can imagine, and we leave our laser unblocked. So this produces now a pulse train of about 40, 50 femtosecond pulses with a wavelength of 800 nanometers, and they arrive at the electrode at every millisecond. And now we just collect a voltammogram. So this is what is shown here for a platinum microelectrode. The CV in the dark is shown in black, and the CV in red is under illumination, right? And for those of you who've done these kinds of experiments before, the usual way this is interpreted is that one sees current features consistent with the different single crystals, right? A microelectrode is a combination of these different single crystal surface structures. The signal is obviously small, but if you zoom in on different regions, there's some very suggestive physics, right? So if you zoom in now near hydrogen evolution, what you see is that if you look at, say, a constant current density and you increase fluence of the laser pulse, you go from 0 up to 3.3 millijoules per centimeter squared, that the onset potential of hydrogen evolution goes more and more positive. Similarly, if you stayed at a particular bias, say, I don't know, 0.02, and looked at currents, the hydrogen evolution current would be larger under larger illumination. So this is now the first observable. If you move now out towards this UPD region, you see something perhaps a bit more curious, right? So the first thing is shown up above, and that is that there is a laser-induced current only where there is existing current features, right? So it's very small if you move out here into the double layer. And that if you look at these UPD features, what you see is that increasing laser fluence, so once again, the black is 0, increasing laser fluence results in a decrease in current going in both scan directions. So how do we interpret this? Well, we can at least say that this signal near 0 volts is consistent with a hot electron-driven reaction, right? There's, once again, this is something that Wolfgang Schmickler has written on. But this signal in this under potential deposited region is a bit more puzzling, right? It is immediately clear it's not chemistry, right? It's not redox chemistry that we're driving. The picture is, if we look at this picture, right, you can satisfy yourself of this. From the point of view of the laser and the electronic structure of platinum, the scan direction doesn't matter. And so the idea is, of course, that this pump pulse should excite the anti-bonding platinum hydrogen orbital going in both directions. And if this is being populated in both directions, there is, the current is flowing in only one direction, right? If we're driving this kind of electron transfer induced chemistry. So what is it, this feature? How can we explain this? Well, you should, first, we got worried that we didn't know what we were talking about, and perhaps we were just seeing an artifact, right? There's all sorts of things that can happen in this experiment. So we start to try to measure the dependence of this hydrogen evolution, photoinduced hydrogen evolution current, and this UPD current on illumination intensity. This is what's shown here. We also now tried to repeat the same experiment with longer pulses at 800 nanometers, with different photon energies, and with CW radiation. And what you see quite clearly is that the size of the signal we observe depends really critically on the length of the pulse. So it's this few femtoseconds, the shorter the better, and that it's a bit sensitive to photon energy, perhaps, right? So what I want you to conclude from this is that this scaling is two things. The first is that the plot on the left suggests the scaling with fluence is inconsistent with heating or bulk photochemistry, right? This kind of saturation is not what you would expect for if either of those two things were happening. And that this dependence of the signal on the femtosecond length of the pulse suggests that whatever this thing is at UPD potentials, that it is at least hot electron related. Okay, so what can it be? Well, then you start to go back and kind of read the literature on this, or we tried to go back and read the literature on this. And you end up with this challenging quantity of electrosorption valency. So the idea here, of course, is that an ion of some valency can absorb when it absorbs on a metal surface, it is expected to discharge to some extent. But quantifying this discharge can be very difficult, right? In this sort of standard electrochemical experiment. The problem is that it can be, of course, fractional, right? And we lack independent knowledge of the adsorbed number and the extent of discharge of the adsorbed ion. Additionally, of course, there's the problem that when an ion discharges, the interfacial dipole changes, and one might expect local solvent structure to change and the total dipole of the interface to change as a consequence of this ion discharge. So there should be a capacitive contribution to this measured current as well. So you can write some math. This, in fact, comes from a paper from Schmickler and co-workers. You can describe this as a change in chemical potential of the hydrogen, right, of this platinum hydrogen complex, and from an ion discharge component, this ID component, and from a dipole reorientation component. And the important point here is that this laser excitation offers a kind of unique ability to address this kind of discharge, right? So we think it's quite clear the whole thing is reproducible. We think it's quite clear from the sign of the signal that we see that we do not drive reduction or oxidation with this laser pulse going both ways. This is inconsistent with the sign of the effect that we see. If you dig into this ion discharge term, you have this valence, this extent of discharge lambda, and then this G term, which is this potential gradient across the double layer compared to that across this adsorbate. And the critical point to note is that the laser excitation only decreases this ion discharge term, right? The population of this antibonding orbital can only make this thing smaller. Of course, we have no idea how the solvent dipoles respond from this measurement, so it can either increase or decrease this dipole relaxation term. Okay, so this seemed a nice framework, and then we said, well, what happens if we now try to look at better defined surfaces? So we did the same experiment. Gregor did the same experiment. Now for platinum single crystal working electrodes, and the results are shown here. So the blue is now this laser-induced hydrogen evolution current collected at 0 volts. And what you see quite clearly is that the largest effect on H2 formation is for platinum 111, then 100, then 110, then the microelectrode at its 100 feature. We just happen to measure it there. Interestingly, now, if you look at this UPD feature, if you pick your favorite UPD feature on these 3 surfaces, one sees that this decreases as you go, the size of this effect decreases as you go from 111 to 100 to 110, in that for the microelectrode, it actually flips sign. So where does all of this leave us? So I show you 2 trends in this current behavior. So it is interesting to note then that this laser illumination increases H2 formation for all of these systems, but that the extent to which it increases H2 formation is inversely proportional to reactivity, right? So the microelectrode is more reactive for H2 production than the 110, then the 100, then the 111. It is also clear, right? So that this is this point number 2. If you think about now this reduction of this sign, the sort of logic that I described on the previous slide, what this suggests is that in the case of platinum 111, there is a kind of overcompensation of the interfacial solvation layer to this charge transfer, which does not exist for the case of the microelectrode. And we can discuss that. And this appears to correlate, this effect appears to correlate with reactivity. So it seems logical to suggest that one might need a kind of Goldilocks configuration of solvent molecules to produce a more reactive surface. So here I just sort of summarize what I have said before. So we think we can induce 2 effects. One is H2 formation, presumably by this TOEFL mechanism, for reasons we can discuss. The other is charge transfer into an antibonding orbital. Both of these effects are clearly surface and electrolyte structure dependent. Okay, so this is great. The time will just work out. So I told you that if we are going to do this experiment on platinum, we need to be able to probe the platinum hydrogen vibration. This is what I show, or platinum hydrogen structure. I showed you we can do this by probing platinum hydrogen vibration. We need to be able to also initiate charge transfer. I showed you we can do this by this 1 photon excitation and the detection of photocurrents. And in the last few minutes, what I want to do is put these together into one experiment. So I want to excite with this same femtosecond optical pulse and probe the platinum hydrogen spectral response. So this thing is shown here. What we do now is combine this thin film sound frequency, in this case with a 1.56 eV pump pulse. Okay, if you do this over the infrared region that I showed before, and you just integrate overall the intensity, you find a signal that looks like this. There are several features that are worth maybe noting. The first is that for ultra-fast timescales, that one sees an increase in absorption near time 0 that lasts, say, a few hundred femtoseconds at all potentials, right? So within the double layer at 0.8 and 0.5 versus RHE, and also within this UPD region. It is clear, though, that if you look at somewhat longer time, so this is delay in femtoseconds, so this is now a few picosecond delay, that there is a kind of offset here, which only occurs within the UPD region. So now, if you are within the UPD region, you have a rapid increase, which seems to persist to somewhat longer timescales. If you now also look at, say, it becomes more apparent as you get into the UPD region at, say, a few hundred femtosecond timescales, it's clear there is a large dip, and presumably this is related somehow to structural dynamics. So this is interesting, right? So this tells us something perhaps about what's going on. But of course, we collect the spectrum in each of these time steps. So we don't need to integrate just the intensity. We can actually look at the spectrum that underlie this. So this is what is shown here. So the top is the static spectrum. So now this is a 1-1-1 surface, but because of difficulties in assembling the cell, it's more defect rich than the previous one that I showed you. These experiments are very long, is another part of the problem. And what I've shown here now is the spectrum. So blue now is an increase in absorption due to the pump, an increase in intensity of this underlying spectrum, and a red is a decrease. And what you see quite clearly is that if we're within the UPD, right, here is this several picosecond long feature that's apparent in the intensity spectrum, right? This extends, the blue extends to a few picoseconds over most of the frequency range of interest. But there is this cutout in the center of the spectrum. It's right around the 1-1-1, the frequencies we've assigned to this 1-1-1 facet, which appears to be depleted in population at most timescales, right? It has this initial increase, same as everywhere, but then you rapidly see this red. There is no communication, right? The easiest way to interpret the signal, the simplest interpretation, is that there are multiple different types of surface hydrogens, and that within the UPD, most of these can exchange on few picosecond timescales, but that there's something special going on with these 1-1-1 facet frequencies. This special quality, whatever it is removed as you approach 0 volts versus RHE. So now here, apparently this type of structural site can communicate on ultrafast timescales with all the other sorts of top adsorbed hydrogen. Okay, so where does this leave us, right? It is pretty clear that at around time 0, there's this strong laser-induced increase in the spectral feature. The easiest way to interpret this is that one increases population of adsorbed hydrogens on ultrafast timescales, presumably because you supply a pulse of electrons to the interface. On about 200 femtoseconds, there is this thing that looks like a U. This is apparent on all at all potentials, right? It seems to suggest that this increase in population results in a rapid exchange, a rapid site exchange of different types of adsorbed hydrogen. And this U it also appears to be insensitive to bias. If you go out to about 500 femtoseconds and longer now, it appears that there is a laser-induced decrease in this 1-1-1 atop adsorbed population within the UPD. But then near 0 volts, this decrease in population does not occur. So whatever this diffusion, this site exchanges can happen for this site only as one approaches 0 volts versus RHE. So this is just an attempt to explain this, and I apologize, everyone's been here a long time, as an attempt to explain this in a kind of cartoon form. So what we think happens within the UPD, within the hydrogen adsorption region, is that there can be multiple types of adsorbed hydrogen, and that at least one, this platinum 1-1-1 facet, appears not to exchange with other kinds of species. We can discuss whether it should exchange here or not. Whatever the details of this surface stabilized state, it is apparent that as one approaches 0 volts on ultrafast timescales, this stabilization is gone. On ultrafast timescales now, this particular type of surface adsorbed hydrogen now can exchange with all other surface adsorbed features. So what I want to suggest now is that this change in mobility is related to, is the causative factor of the onset of H2 generation. So one way to understand what's happening, or one hypothesis of what's happening as one starts to produce molecular hydrogen on platinum, is that this thing is the active site, and that whatever the processes are which allow increased surface mobility right near 0, that this it now is possible, and so that this thing can participate now in hydrogen generation is possible. So you might say, well, what other evidence is there for 0 volts being special. There are a couple of theory papers, theoretical studies now, which seem to sort of point in similar lines. I like in particular this recent one from Neugebauer and Todorova and Sudarshan Sarandralal, where they calculated what they describe as the work function. So it's a bit complicated if you're not a chemist. So what is plotted on the left is the work function. So this black line is the experimental work function in vacuum. This is the energy it requires to inject an electron to the vacuum level as a function of hydrogen coverage. One way to interpret a CV is that it is an effective work function for the electrochemical environment. And if you do that, you can write then the experimental work function for the electrochemical environment. This is shown here in these black X's. So the specific thing that they add, they would argue, I think, to this is added in this contribution is that they have a scheme to really reference their electrode with high precision. And if you do that, what you find is that as you approach about 0.6 monolayers of hydrogen, so this is the surface coverage of hydrogen at 0 volts RHE, that the surface becomes very unstable, right? And that the hydrogen starts to desorb, and that the system wants to jump back to this similar work function describing the vacuum adsorbed case at high coverages. So you might say, well, what causes this jump? Well, they would argue it's shown here. So you can decompose this calculated work function into a component that's due to hydrogen adsorption on platinum. This is what's shown in blue. A component that's due to water orientation. This is what's shown in green. And then a component that's due to chemisorbed water, so electron transfer from water into the platinum electrode. And they conclude in this paper that as one increases hydrogen coverage, one displaces chemisorbed water, and you lose this stabilization of the interface that chemisorbed water affords. And so this then it would suggest that the mobility and the site exchange of platinum should increase dramatically as one approaches this magic 0.6 monolayer on 111. This is in fact what they observe in simulations, and is consistent with this picture that I just told you. Okay, so this is really the end. Wow, it's great, it's right on time. So where does this leave us for hydrogen evolution on platinum? Well, I want to say that I want to contend that I've shown you that femtosecond optical excitation can be used to induce hydrogen formation on transfer, H2 formation, charge transfer. This is a function of solvent structure. That time averaged spectroscopy suggests top adsorbed hydrogen exists for all of the UPD region. This is consistent only if sites exchange on these macroscopic timescales. We sample in that measurement. But that on ultra-fast timescales, it's quite clear that all of the sites do not exchange, and that the onset of macroscopic activity correlates with a real change in these ultra-fast fluctuations of hydrogen adsorbed on platinum. So at least the photocurrent stuff is already out. The other stuff is in prep. Okay, so I thought maybe we just end with some more general conclusions, since we've only talked about hydrogen evolution on platinum. So I've tried to show you today sort of two examples of how you can gain mechanistic insight into reduction chemistry on metal electrodes by generating populations of hot electrons that then populate antibonding orbitals and for adsorbates, or adiabatically transfer into water. Of course, you can do this for semiconductors also. So on semiconductors, we work on this, and a variety of others have shown that you can employ femtosecond optical excitations to create, to drive oxidation chemistry, to create holes at the interface that can accept electrons from solution, or reduction chemistry, create electrons that can be donated into solution. The challenge here is, of course, that many of these carrier dynamics in semiconductors are quite long-lived compared to metals, so that you can have relaxation processes within the semiconductor that are unrelated to electron transfer to solution that happen on the same timescales. But of course, there are ways to deal with these problems. So I just maybe end with our worldview is that if you want to experimentally characterize electrochemical mechanisms, you should be doing experiments like this, right? That you should be doing perturbation experiments as fast as you can, basically. And that at all timescales, this is useful because it's the best way to separate this multi-timescale continuum that contributes to steady state reactivity. So the kind of long-term, vision of where the world should go is, of course, you might ask yourself, how do you deal with heterogeneity, right? So I've shown you a lot of stuff on well-defined polycrystalline films or single crystals, but of course, most of the things you really want to work with are, spray cast amorphous materials that might be useful, that might be cheap for large-scale device production. And the distinguishing factor of such materials is that they're heterogeneous structurally on all sorts of spatial scales as well. And this would suggest that where we should go, or where the community should go, is towards experiments that offer nanometer spatial and femtosecond temporal resolution. And we can talk about what such an experiment might be if you like. Okay, that's all I have. Thank you very much for all of you who stayed around. It's nice not to be completely alone while you're talking.
Thank you so much. Anyone has any questions? So we're open for questions. Maybe I can start by asking a few questions from the YouTube chat. So just to again clarify, I guess you already said it, but I think it's better maybe to repeat it again. So the question is, does the laser pulse itself induce any change in the double layer structure? Maybe you can just make a comment on that and again explain.
Yeah, I mean, this is, of course, this is the point of, this is the point of this discussion here. So what I understand this to be asking is, if you change the double layer structure, you are changing the capacitance of the double layer. And this experiment illustrates quite clearly that you do. But this is what you would expect, right? So if you in fact induce charge transfer, you would expect that you change the double layer structure.
I guess no. So I guess the question is whether your laser pulse can change the double layer structure such that you sort of drive it out of equilibrium. I presume that it shouldn't, because the time scale is very different. So the thermal excitation that it brings into the double layer that restructures as a result is far,
right,
on a longer time scale than your actual charge transition.
So maybe a couple of points are worth noting. So one is, of course, that there is no cumulative effect in the experiment from pulse to pulse. Mm-hmm. So that this is the first point. So whatever you do 1 millisecond is gone well before the next laser pulse arrives. Then the question, I guess, is things like heating. And you can do, the issue here is that we are exciting the metal with photon energies, which are absorbed only very weakly, if at all, in the solution. Mm-hmm. And so the specific heat capacity of electrons and metals are very small. And so the total heat change that you do by this excitation is pretty tiny. So we have done similar experiments earlier, not in an electrochemical environment, but where you add an infrared pump to this vibrational sum frequency probe. And the idea there then is that you want to say something about vibrational dynamics, mm-hmm, with interfacial resolution. And in this case, you actually want the medium to absorb as much of the pulse as possible. And you can calculate then, in this case, you do heat the sample, and you can calculate that it's something like a 10 Kelvin increase in temperature over the laser focal spot, but that heat conduction is your friend. It diffuses out into solution before the next laser pulse arrives. So even in that experiment, there is this mismatch in timescales that you describe, so that the thermalization happens on about 5 or 10 picoseconds timescales for direct resonant excitation in solution. Mm-hmm. And so all the stuff that happens faster than this sees the unperturbed structure. But again, the measurements that I showed you, the experiments that I showed you here are with laser photon energies, which are not absorbed, are very weakly absorbed by the solvent. So they're the direct heating effect on the solvent is very weak.
Great, thanks. I think that another question is relevant for the intermediates. So the HR is a fairly simple reaction from the perspective of the people who work in electrocatalysis. So for example, there are many questions about the intermediates for the CO2 reduction. So do you see that this methodology can be applied or can be extended quite efficiently to detecting the intermediates at the surface for the CO2 reduction?
Yeah, I think it's even better. I mean, actually the situation is a little bit, so we do a bunch of work on hydrogen evolution and some on the OER as well. And as you say, hydrogen evolution is not so complicated, although I think we struggle to understand issues like the pH dependence, the sort of underpinnings of the pH dependence or electrolyte effects on hydrogen evolution rates. The OER is obviously a lot more complicated, but most of the interesting intermediates, at least from a vibrational perspective, are at quite long wavelengths. So this sort of peroxo species, which makes the experimental challenge, makes the experiment a little more challenging. Mm-hmm. But all of this kind of small carbon molecule chemistry is pretty straightforward to probe in this probing scheme. So we've done a bunch of work with formic acid oxidation in a steady state probe, and are starting projects on urea oxidation and have a proposal on alcohol oxidation as well. The issue in doing this time-dependent question, if you actually want to drive the reaction through to completion or through at least to desorption, mm-hmm. is whether what the concentration of reactants is in the system. So of course, the logic of this experiment is a kind of pump probe, is a pump probe one. And what this means is that the system should be back to zero each time you have a pump pulse, right? And obviously, if you have a very dilute solution, then this will not be the case. You will the next reactant molecule will not diffuse in on a rapid timescale. There are ways to address this from the timescale of from a kind of experimental setup. So in the typical probe scheme, you take many photographs at many delay times. But of course, you don't need to do this, particularly if the reaction is the kinetics that you're interested in extend to much slower timescales. You can do one pump pulse and follow it by several probing events. Mm-hmm. And so for more dilute systems, which do not, where the diffusion of reactants to the interface is slow, one would have to think about ways to overcome this problem.
Sure. Okay. I guess the time is almost up, so maybe I will just ask the last question that I have, because I think you mentioned at the beginning, and I'm just curious about your opinion. So you mentioned the following, that the electronic structure of the bulk solid is important. So it's certainly the case, but when you come to the surface, there could be surface states, there could be surface electronic structure, which is might be quite different from the bulk. So we know this from different materials, not only metals. Now, if it comes to the photo emission experiments in the UHV conditions, so we know that there is a significant dependence on, so we can basically probe the photoelectrons, and depending on the angle, we can then deduce on the Fermi surface, the K vector, and so on of the electrons going out. Now, this is sort of the state of the art of how we can study this electronic structure of the surface. But in the photo, so in the PES experience, the photo emission, we use also the optical pulses that we induce these electrons. We kick them out and knock them out of the solid. But you do exactly the same in some way, but in liquid. So I'm curious, is there any way that you can breach your experiments in terms of the electronic structure of the solid? Not like just a sea of electrons, but more of a specific band structure, and the specific Fermi surface even, to what people do in UHV conditions.
Okay, so maybe two things about this. So this, I mean, first, of course, what you're describing was what I tried to, but maybe didn't describe too clearly before.
Exactly. This is why I'm trying to bring it up back again. Yeah.
So this kind of state-of-the-art photo emission experiment here is one that you do with a small layer of liquid on top of the metal. Now, this will not work for perhaps all of these things. You have a mass transport problem if you actually want to produce products in this very thin layer, right? Yeah. So it will be very challenging if you're actually producing, doing chemistry to actually do that kind of measurement. But at least for issues of electrode polarization, because of partial charge transfer, this kind of experiment should be possible. I mean, if you have one, let's say 1.5 million to spare, Specs in Berlin will sell you a setup to do this. Then you just need the laser, right, to add on top of just the laser. The other question is how you address this optically. So here, of course, if you do the kinds of optical experiment, I mean, you are limited by the fact that photons don't carry a lot of momentum. So you are always near the gamma point, right? You will not see the Fermi surface, with one exception we will get to in a second. But within this restriction, of course, you can do the kinds of measurements that, first of all, you can move to different ranges of photon energies. So we work now on making this some frequency measurement resonant in the visible. So doing a kind of, in this sense, now it becomes an electronically resonant some frequency experiment and not a vibrationally resonant some frequency experiment. And this then is sensitive to optically accessible transitions, say within the band gap of semiconductors. So it seems to be a promising way to directly address surface states, the electronic transitions that underlie surface states. So this is maybe one point. If you want to gain some extra momentum, you have to be a little bit creative about in the optical experiment, you have to be a little bit creative about the sample geometry, right? So you have to use a so-called auto geometry where you use some kind of near field where you bring, say, a grating or a prism very close to the electrode surface, which gives you extra momentum in the plane of the surface. And so you would need to do something like this to gain any kind of momentum resolution, for either electronically or vibrationally.
Okay, so it's pretty complicated, at least.
No, I mean, but people should do both. I mean, I don't need to say that everyone should only detect photons. I mean, you should detect electrons as well, right? I mean, I think that this is, I was sort of, I hope lots of people have the 1.5 million to spare to get this out from specs. I think that both approaches are important, right? To sort of reveal the full physics of what happens.
Mm-hmm. Mm-hmm. Okay, we have a comment in the chat that I can read out, and maybe at that point we will end. If you want to comment too, you can do it. So the comment is the following: just in case, at the potential less than 50 millivolt versus RHE, a lot of H2 is formed even without elimination. So there are no gas bubbles, just dissolved molecular hydrogen. The quantity of this hydrogen depends on the time of the potential static treatment or experiment. And the formation of molecular hydrogen will continue up to the point when we reach equilibrium pressure inside the electrolyte. So
I mean, this is of course true, right? So in order for us to do this experiment, because we do optics, we are screwed if bubbles start to show up on the electrode. So then there's all sorts of scattering, and it becomes very difficult to actually know what the photons are that are reaching the interface and detect the emitted field from the interface. So we try to operate in a situation in which H2 production occurs, but is sufficiently slow that bubbles are not generated. We also operate in a flow-through cell. So this kind of accumulation to supersaturation and then bubble nucleation, either on the surface or homogeneous nucleation in solution, we don't want.
Oh, surely I do not mean that it's gas evolution. I mean that molecular hydrogen is in solution. We can discuss later because now people are very tired, and if you like, we can discuss by correspondence.
Sure, I'm happy to.
Okay, thank you so much. Then at this point, we're going to wrap it up for today. So thank you, Kramer, for joining us and for being with us for especially so long. I think it was really interesting. I would say a pretty rare presentation on the pump probe experiments. There are probably not so many groups who are still working on this or who haven't yet started. There's a lot of potential.
There should be more, though.
Like you said, we need money. Yeah. Okay. Thank you so much. And yeah, have a nice day, evening, or whatever time you have at your.
Okay.